Okay, this is lesson 10.6 on power series. So what power series is really that we're tacking on these x variables into our original series, right? So our series of numbers, and hopefully this is converging or diverging series, and then we're just tacking on these powers, these x, 1 power, x squared, x cubed, x to the fourth, x to the n power, right? So basically what we're trying to see if this x is going to do something for us, and if we can kind of if we can answer some questions as to what the x's should be, and then to make it absolutely converge, right? So we can restrict the x within a certain number interval, numerical interval, so that if x is between these numbers, then the whole sequence, the whole series is now going to converge. And if it's outside of this interval, then it's going to be diverge, right? So that's really what we're trying to do. Okay, so now we have this sequence paired up with these powers, right? So let's go ahead and see what we do normally with something like this. So it says find all the values of x in which this sequence here is absolutely convergent. So you already kind of have an idea that we're trying to go for absolutely convergent, right? So let's go with something we know already. We are going to go ahead and use a ratio test on this, because this is typically what is easier because you have x to the nth power. So to the nth power ratio test is actually really useful. I know we had a root test before, but a ratio test is actually more applicable in these cases. Okay. All right. So we're going to go ahead and say, first of all, let's take a look. This is our sequence here. This is the sequence, this is the formula. So this is really the sequence of n equals 0 to infinity, n over 5 to the n, x to the n. Okay, all right. So we're going to do a ratio test on this. So limit as n approaches infinity of n plus 1 over 5 to the n plus 1, x to n plus 1. And then again, at this point, you know you're dividing by this original function, so you can go ahead and multiply by the reciprocal. It's a little bit easier. So 5 to the n over n, x times n. And you need absolute value around this because you're not, x is a variable. You're not 100% sure x is positive or negative. So the absolute value will ensure that we're only dealing with positive values. And so that makes it a little bit easier to deal with rather than having to figure out whether or not there's going to be some possibility of negative in there, and this may turn into an alternating. So we're looking at this as if it's a positive value series. Okay. All right. So go ahead and clean this up. We now have limit as n approaches infinity. We still have our n plus 1 on top. We still have x on top because x to the n reduces out. So we have x on top. And then we also have 5 on the bottom, and we have an n down here. Okay. Now, of course, again, looking at higher power rules, you have your n and 5n here that will reduce out, right? So you really have, your limit becomes 1/5 and the absolute value of x. All right, so 1/5 and absolute value of x, because 1/5 is not included in the absolute value. It is a coefficient. So you can pull it outside of absolute value. Your variable is what's left, so that's your x. All right. Now, because we want it to be absolutely convergent, we know the ratio test for it to be convergent, it has to be less than 1. So that's why we set this less than 1. Now, this is algebra. We're trying to figure out what numbers, what interval does this number have to be in between so that this actually works as an absolute convergence, right? So then the algebra says multiply 5, right? So you get absolute value of x is less than or equal to 5. And then because it's an absolute value, this becomes a compound inequality. So negative 5, x, 5. So really your interval is negative 5 to 5. All right. We like to write these as interval notations. Now, we're not done yet because you need to check your endpoints. You need to check your endpoints at negative 5 and 5 to see if they do converge or not, right? If they don't converge, then we don't include these endpoints. But if they do converge, we now need to close those endpoints. So we just need to check these endpoints. All right. Now, we need to plug it in back. We need to check those endpoints by plugging it back into our formula. So we're going to check x equals negative 5. We're putting it back into this sequence here. So we're going to say limit as n. Oh, we don't need to write all that. We know it's going to be the same exact thing. Save yourself some time. So it's n over 5 to the n, and then x is 5. So negative 5 to the n. Now you have negative 5 to the n here. What it's going to do is it is going to split it up, right? If you remember your algebra, negative 5 to the n is really negative 1 to the n, and times 5 to the n. Or actually, let me try to back that up. This is really negative 1 times 5 all to the n power. This is really negative 1 to the n, 5 to the n. So why am I doing that? Because then that 5 to the n will reduce out the 5 to the n on the bottom, really leaving you with an alternating series of n. Okay, alternating series of n. Okay, now you can do the alternating series test right now, right? So usually these at the endpoints become a little bit easier to do for our testing. So we're going to go ahead and test and say limit as n approaches infinity of this, of n, because it's an alternating series test. And this will be infinity. So this is diverging by alternate series test. Okay, so that's one endpoint. How about the other endpoint? X equals 5. So x equals 5, my series becomes n over 5 to the n, and then 5 to the n. Okay, so these go away. You're left with a series of just n. What is this going to do? It's going to diverge, right? Because it's just going to go on. It's n plus n plus n plus n. So 1 plus 2 plus 3 all the way to infinity. So this is also infinity, and this is also divergent, which means then my interval is not inclusive of my endpoints. Okay, all right, that's it for this then. All right, moving on. So this is kind of cool. The theorem says that if you do have a power series, then you have exactly one of the following. If the series converges, if only if x equals 0. So what you're doing is you're adding infinitely many zeros. So x equals 0, so 0 to the 1 power, that's your variable, right? So you're really just having your numbers here. So you actually are adding a bunch of zeros up with this first number. So 0 plus 0 plus 0 plus 0 plus a number, you do converge. So you know for sure that's a condition that converges. And it'll pop up later, you'll see why. Because if it diverges, if your answer becomes the fact that the whole thing diverges, then you have one possibility, is when the series converges when x equals 0. So if x equals 0, that's one possibility. Okay. Now, the second possibility is that it is converging for every x. So then your interval is going to be negative infinity to infinity, right? So the whole thing is converging for no, you don't have a boundary. You don't have an interval where it converges like we did with the previous example. The third example, condition number 3 is what we just did, that you have this interval where you have convergence. Now, sometimes the endpoints are going to be inclusive. So that's why I'm showing you all these different possibilities of including your endpoints, okay? And this R, this number, this interval that you're getting at, this is called the radius of convergence. It's going to pop up later, I guess. So yeah, we're going to have to look at it. Okay, so what do I do with the problem that's presented to me? Okay, so let's say you have this problem. You have a series of e factorial times x to the n. Okay, so we start the same way we do the ratio test, right? So limit as n approaches infinity, n plus 1 factorial x to n plus 1 all over n factorial x to n. This is not a rational function to begin with, so I can just go ahead and do this kind of division very nicely and see if we clean up a bit. So limit as n approaches infinity, you get n plus 1, and the top is just times x, right? So if you plug this in, what are you going to get? Well, if you plug in the limit, you're going to get infinity, right? So then this is diverging. But wait, if this is diverging, we still have one case that this works. It is when x equals 0. So then so it's all diverging, always diverging, except one case. So it only converges if when. All right, when x equals 0. So that's the case that it works, right? So if you get diverging, you got to keep in mind there is a case that it will converge when x equals 0. Okay. All right. Next example, we have the series of 1 over root n x to the n power. Okay. Ratio test. Limit as n approaches infinity, you have x to n plus 1 over n plus 1 square root times the reciprocal of that, so root n over x to the n. Okay, don't forget absolute value because we don't know what x is. Oh, I forgot my absolute value here. Okay, no worries. Okay, clean this up. We get x, and then you have root n over root n plus 1. Again, higher power rule says this will reduce out to be just 1. So you have your x times 1, right? So you have your absolute value of x. So remember absolute value of x, because we want it to be convergent, it's going to be less than 1. So using your compound inequality, you get negative 1, less than x, less than 1. Now let's check, right? We want to check our endpoints. Always check your endpoints. So check x equals negative 1. Oops, sorry, this is way too light, too bright. Okay, so when x is negative 1, what's going to happen? We have sigma 1 over root n, negative 1 to the n power, making this a alternating series, right? Negative 1 to the n, 1 over root n. So we just need check limit as x approaches infinity of 1 over root n That's 1 over infinity. That's 0. So this converge by alternate series test. So for these, you don't need to check if it's conditionally convergent. If it converges, we want it to be this condition because it's conditionally convergent. Doesn't matter. This is an alternating series. So it's going to be that condition that we need. So we don't need to check for conditional versus absolute. Okay. All right. Same thing on the other endpoint, x equals 1. You have the summation of 1 over root n, x is 1, sorry. 1 to the n power, which doesn't really do anything for me. So I'm looking for 1 over root n. Okay, so we have the summation of 1 over root n, and that will be n to the 1/2 power, right? So this is 1 over n to 1/2 power. Since p is less than 1, this is a divergent series. So this is a divergent p series. So that means then that endpoint is not included. So the only inclusive one is this one, right? So now my final interval that I'm looking at is going to be between -1 and 1, inclusive on the -1, but non-inclusive on the 1. Okay? All right. So now this says not all power series are centered at 0, the center of the interval. So meaning that, look at our interval here, right? 0 is in the center of this, and 0 is in the center of this. So what happens if we shift it a little bit? It just means that number line got shifted a bit, right? So what are we going to do? So that x minus 3 is going to play a little bit of a role in here, and you're going to see how that is going to affect my final answer. Okay, so we do start the same exact way, and the definition is all the same as well, except that now it says it converges if x equals c. So you're really just solving for x minus c equals 0, right? So that's condition 1, and there's condition 2. It's always absolutely convergent in the entire thing, in all x's, so in negative infinity to infinity. And then you have this c minus the radius plus c plus the radius. So basically your interval is going to change a bit, and again checking the endpoints, whether or not you have some inclusive or non-inclusive endpoints. Okay, so same thing before. This is where my sequence is. So this is my series here. This is really n, well, it doesn't really matter what n equals, but this is going to be -1 to the n, 1 over n plus 1, x minus 3 to the n. Okay, so this algebra can get a little bit extensive in this case, so just kind of watch out for what you're doing, okay? All right, so we're going to do the ratio test. So limit as n approaches infinity, -1 to the n plus 1 power times x minus 3 to the n plus 1 power, all over n plus 1 plus 1, so n plus 2, okay? Divided by the original series, or multiply by the reciprocal. So you get your n plus 1 up top, -1 to the n power, x minus 3 to the n power down here. Don't forget your absolute value because we don't know what x is going to be. Okay, clean up. Let's see how strong your algebra is. All right, so the top will give me -1 to the 1 power, because -1 to the n is reduced out. Then you have x minus 3 to the 1 power. Then you have n plus 1, and you have n plus 2. Okay, so the thing is, because of the absolute value, that -1 to the 1 power is gone. It doesn't matter because absolute value -1 is +1, right? And then your higher power theorem says those two will reduce out to be a 1. So you're really looking at absolute value of x minus 3, right? So remember, we want this to be convergent, right? So absolute value of x minus 3 is going to be less than 1. So you create now your compound inequality. So -1 is less than x minus 3, less than 1. Add 3 to both sides, so you get 2x, 4. So x is between 2 and 4. Now, check your endpoints. Okay, so x equals 2. What do I get? I get summation of -1 to the n, 1 over n plus 1. Now, 2 minus 3 is -1 to the n. So this is really awesome because now these two are just going to cancel each other out. It's going to make it positive, actually. So now I'm left with just this equation here, right? So what do? I use a limit comparison test to check this series, see if it converges. So I'm going to compare, go limit as n approaches infinity, 1 over n plus 1 over 1 over n. That makes it 1 over n plus 1 times n over 1, which is just 1, right? So now, because they're the same, I can say that 1 over n is divergent p series. So therefore, 1 over n plus 1 is divergent by limit comparison test. Okay, so that is true. All right, so that's divergent. Then I don't need to worry about that endpoint. How about x equals 4? Okay, so that's the summation, sigma, -1 to the n, 1 over n plus 1. All right, 4 minus 3 is 1 to the n. Okay, so that means then this 1 to the n doesn't do anything for me. It's kind of gone. So this is an alternating series, right? 1 over n plus 1. So because this is an alternating series, I just need to check limit as n approaches infinity of 1 over n plus 1. That gives 1 over infinity. That is 0. So it is convergent by the alternate series test. So therefore, this endpoint is inclusive. So we're going to include this endpoint right here. So my final answer is going to be 2, 4, inclusive like this. Okay? All right, that's it for the examples today.